up to this, just if I if we puzzle between these two and these two, NMR will save us. Just record the J value. It will have small J value. Here we have a large J value. Large J value. Again, just for what is Z value? The separation between these two peaks is called Z value. The coupling constant. It doesn't depend on the instrument or machine or frequency you are using. Whatever the frequency is 60 megahertz, 90 megahertz, 500 megahertz, 600 megahertz, more than that, the Z value will be same. Then it can save us or it can just remove our uh, difficulties in identifying two compounds. But if we have two different things, let's say we have one alkene, one is trans and one is cis, then what to do by NMR? Think about these things. We have these alkenes, C double bond C, let's say Cl is here and C double H, and yeah, Cl, C double H, H. You have contaminated, you have just been puzzled which alkene these things or how to distinguish these two alkenes by NMR. How to differentiate? Very interesting point. Differentiate by NMR. Then what's the rule? So we have to see how the coupling depends. Now we see that here is a protons, the proton will couple to each other. Here we have, let's draw it here carefully. H. Now both case, what we will get, we'll get a coupling between these two. Here it is coupled, trans coupling, because the coupling between two trans hydrogens, and here is cis coupling. So coupling between two cis hydrogen. Now we'll have a look on the mechanism of coupling. How does it do? So let's see. Just I will not discuss in that much details, but you have to remember or you have to just believe one thing. Coupling is not through space. Coupling is a through bond effect. So you have to believe me, but I don't have any at this situation to explain this now. Why? It's a quite rigorous mathematical calculation that will part some different things, but just believe this statement. Coupling, a very interesting statement, very important statement. Coupling occurs through bond, not through space, not through space. So coupling occurs through bond. That's why it's in this direction. It will occur here, here, and here, 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 here. Now the questions. See, 1, 2, 3, 1, 2, 3 is basically called. So 1 bond, 2 bond, 3 bonds. It is called 3 J coupling HH. We designate at this 3, 1, 2, 3, 3 bond coupling designate as between two protons. So basically it's also 3 JHH. So it has been given the coupling value is 3 JHH. Oh no need to worry about that. Here also look 1 bond, 2 bond, 3 bond. So here also 3 JHH and 3 JHH. 1, 2, 3, 4. So this is 3 JHH? No. This will be 4 JHH. 1, 2, 3, 4. 4 bonds. Okay. So now we know that coupling occurs through bonds in such a fashion coupling occurs, and in such a fashion, but not through space. Then how? What is the orbital interaction during the coupling? Okay, if the orbitals align in parallel way, then the coupling will be better. So orbitals have to be aligned in parallel manner. Orbitals have to or has to align in parallel manner. So we'll have a look on these things. Look, let's say, so this is the orbital here, C double bond C. So this one here, H Cl, and here look, yeah, H. These orbitals are located in a parallel manner. Look in this fashion. So parallelly aligned. So here we expect more coupling. More coupling. So now if you ask me why parallelly aligned orbital coupled more, that is at this stage is not beyond our scope. No, sorry, is beyond our scope at this stage. But if we get later time, I will discuss why parallel coupling is most. So is parallelly aligned. And look at here, orbital for cis1. So this is, sorry, yes, C double H, C double H, H. So this will be uh, H. Just draw the orbitals. Just I put it here. Just also cover the hydrogen also. But here it's not parallelly aligned. So here not parallelly aligned. Not parallelly aligned. Hence here coupling weak. So what we observe, trans coupling stronger in nature, stronger in nature, and cis coupling respectively weaker. Weaker comparatively, I should write comparatively. Comparatively in nature. As this is trans coupling stronger in nature, that's why what is the Z value? We know it is JHH. So JHH will be higher here. So this will be here almost 15 hertz. Look the value 15 hertz. And here the value is around quite low, around 9 hertz. Around 9 hertz. So how to detect? In both case, you have a doublet. Think here, in both case, we have a doublet. Here also have a doublet. Where the separation between these two doublet, these two peak in doublet will be more. That is for trans one. This is for trans one, and this is for cis one. So also fantastically, you remember also we can detect or differentiate the two protons in alkene by R spectroscopy. Now here we more prominently can detect or differentiate two alkenes, cis or trans, by NMR spectroscopy. Very much interesting. Just look at 3JJ value, 3JH value. For trans, it is going to 15 hertz. Look at the separations, which is more, that is the trans one. And for cis, the separation is 9 hertz. Highly interesting. I hope you are enjoying a lot. So this is the way we can differentiate 12 keys. So what we learned it here. So first one point is that Also, we are learning by statement also with the basic theory rather than solving problem. So coupling occurs through space, and if the orbitals has parallel alignment, then the coupling will be stronger. So in case of transalkene, we have parallel alignment of the orbitals. That's why it's stronger in nature. That's why we have higher 3 ZHH value, 15 Hertz. For cis one, weaker compatible in nature because their orbitals are two CH bonds